Yeah, welcome to the Algebra 2 jungle, and we're going to jump into some arithmetic series. Now, basically what we're going to try to do tonight is really try to combine the last two nights. 2 nights ago, we focused on an arithmetic sequence, which, and this will shock you, a sequence is not the same thing as a series. And then we're going to try to combine it with the summation sigma notation that we worked with last night, and you'll notice that right here. So we're going to try to blend the two ideas together. We're going to define what a series is, why it's different than a sequence, and how we're going to combine it in conjunction with the summation sign. The best news I can offer right now is that we're not going to worry about geometrics tonight. We're just going to put 100% of our energy into arithmetics. We're going to revisit how to write them recursively, how to write them explicitly, and jump in from there. So right off the bat, here's our $1 million question to kind of set the tone. What the heck is the difference between a sequence versus a series? I think a lot of times we kind of jump the gun and we treat these words as if they're synonymous and that they're one and the same, but they're drastically not. A sequence is simply a list of numbers that are separated by comma signs, and they happen to have a specific pattern usually. So, for instance, we might go 3, 7, 11, 15, etc., etc., etc. And here's a sequence that happens to be arithmetic that has a common difference of what? Yeah, hopefully you said it had a common difference of 4. Now, a series is now a sum. Got an extra curl in there, of the terms within a sequence. So basically now it's 3 plus 7 plus 11 plus 15 plus etc. And this year all of our series are going to be finite. In other words, they'll actually finish with a number. And then when we get to Calc 2, they'll start to be infinite series, and we'll take them all the way to infinity and go from there. So to summarize what we got cooking here, a sequence is a list, and a series is the sum of the numbers within that list. So here's the definition that I want to expose you to tonight. Definition of a series. So they're saying if the set, and I'm going to put some squiggly brackets around it, a sub 1, comma, a sub 2, comma, a sub 3, comma, dot, 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 boom, boom, boom. So basically what we have here is we are defining a sequence right here. And the reason you know it's a sequence is because it's just a list of numbers separated by commas. If they represent the elements of a sequence, then the series, and I'm going to use a capital S with a subscript of n, is defined by blank. So I'm going to say S sub n is the sum of a sub 1 plus a sub 2 plus a sub 3, okay, plus we'll say dot, dot, dot until we hit a sub n. Or we could write that as summation notation, which would look like let's see, we got sigma for our summation. I'm going to use the index of k. A lot of times you could use the letter I or a variety of other letters. I'm going to say k is going to start with 1. It's going to work its way up until it hits n. And we're going to use a subscript k. So what does that mean? Well, it's the sum of a sub 1, which corresponds to this term, then a sub 2, a sub 3, dot, 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 all the way until we get up to a sub n. This n here corresponds to the n there in the last term. Here's a real quick recap of the recursive formula for arithmetic versus the explicit formula for arithmetic. I thought 2 nights ago was really, really tough. We did so much arithmetic and geometric stuff all in one night. It was very, very challenging, and kudos to you guys for hanging in there. So a recursive formula says, and I'm going to use this notation to start off with the subscripts. The nth term is defined as the n minus first term plus the common difference. Okay? And we're also assuming that a subscript 1 was given. Alright, now if I was using my functional notation, I'd say something like f of n, also representing the nth term, is defined as the n minus first term plus the common difference, where f of 1 was given. Okay, now if we do an explicit formula, now we're saying that the nth term is defined as the quantity n minus 1 multiplied by the common difference, then added to the original term. Or using my functional notation, we could say f of n is, let's see, whoops, I don't want that f there. Let's see, okay, again it's n minus 1 multiplied by the common difference, but then adding to the original term, which is just denoted a little differently. Probably what you're going to see me do for the rest of the video tonight is you're probably going to see me use the subscript notation, but I also always want to just continuously expose you to the functional notation just in case. Alright, let's get things cooking here. What they're going to do in the next series of problems is they're going to describe an arithmetic series here in each problem, and sometimes they're going to give us more information than other times. So this is a very nice one to warm up. They said the first term is -2, the common difference is 5, and there are 20 terms within the sequence that they want us to add up. So I'm going to ask you to do the same part A, B, and C for a bunch of these. We're going to write the recursive formula based on this general form. Then we're going to do the explicit formula based off of this rascal. And then the really new part for tonight is for us to find the sum of the arithmetic sequence, specifically finding the sum of the first 20 terms. So without further ado, let's jump into part A. And the recursive says that the nth term is defined as the n minus first term plus the common difference, which in this case is plus 5. Now, the explicit form says that the nth term is defined as the quantity n minus 1, then multiplied by the common difference, and then on top of that we're going to add the original term, which was in this case -2. Now I'd like to clean that bear up just a little bit. We'll distribute the 5 here and get 5n minus 5, and then we'll subtract 2. So the nth term is really 5n minus 7. And that explicit form is really going to help us here with the sum. Now they want let's see, the sum of the first 20 terms. So that's like a sub 1 plus a sub 2 plus a sub 3, yada, 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 plus a sub 20. Now there's no doubt there's a long way to do this. We could do this by hand. We could calculate each term individually and then add up all 20 of them by hand. But I'm going to tell you what, I think there's a better way to do it. There's a quicker way, there's a more efficient way, there's a smarter way to do it. And it involves using summation notation that we talked about last night. And I'm always going to use the explicit form right here, okay? Make a special note of that in your notebook. We're always going to use the explicit form to describe the nth term. And we're going to start with the first term, known as n equals 1, and we're going to keep adding each of those terms up until we get to the 20th term. Now from there, it's all about the calculator for me. I'm going to enter this into my calculator by first hitting the alpha button, and then above that somewhere there's the F2 button, and from that menu we're looking for the second option. I'm a calculator, I'm going to type everything in terms of x, but even though on my paper it looks like n's. And for the sum, I got 910. Now in a quick summary of our game plan, and this is specifically our game plan for finding the sum of a particular arithmetic series. The first thing I want you to do is to find the nth term by writing an explicit formula. Alright? Emphasis on the explicit formula. So technically, if the only thing the question asks for is to find the sum, then we're not going to worry about the recursive part. The only reason I'm really incorporating that tonight is just to review and just really to highlight the difference between a recursive formula versus an explicit formula. Next thing is we're going to rewrite everything in sigma notation. And that's what's going to find the sum for us. And what that's going to look like is we're just going to import the explicit formula for the nth term, and we're going to start with n equals 1, and then we're just going to go up until, and I'll put a little question mark there, whether it's the first 15 terms, first 20 terms, first 100 terms, whatever it might be, the last term goes on top. And then the third step is to evaluate on our calculator. We're going to rely on that tonight. We proved yesterday that we understand the process behind sigma and that we know how to do them by hand. So tonight it's all about evaluating them on our calculator. Now this next question is significantly more challenging than the previous question, and we're about to find out why. Here's the given information. They said the very last term is a sub 12, which happens to be 100. So the 12th term within this sequence is equal to 100, and the common difference is a 4. So the exciting news is they did tell me the common difference. It happens to be 4. The bad news is they did not tell me who the first term was, and we need to know the first term in order to write both the recursive and the explicit formula for an arithmetic sequence. So how are we going to tackle this? What we could do is we could just start subtracting 4 from 100 and do that consecutively for 12 times until we find out who the first term was. But I got a better plan. And that better plan involves solving it explicitly first, and then I'm going to come back and do part A and write the recursive formula really quick. So I'm going to leave a little space here for part A, knowing I'm going to come back, and I'm going to jump right into part B, the explicit. Now here's the kicker. If they told you who the 12th term is, let's start there. And let's say A subscript 12 equals, and I'm going to substitute a 12 for this n. I know that my common difference is a 4. But I don't know who A sub 1 is, so that's the mystery box right there. Now, this A sub 12, who is this rascal? They said it's 100. Okay? And I know that 12 minus 1 is 11, and 11 times 4 is 44. And then I just simply subtract 44 from both sides, and that's going to tell me that 56 is the mysterious unknown first term. So let me back up really quick. I'll get the recursive out of the way so I don't forget it. So the nth term is defined as the n minus first term plus its common difference, where the first term is 56. Now, what does the explicit definition look like? Well, it says we got n minus 1 multiplied by 4 plus 56. If I distribute that 4n minus 4 plus 56, that cleans up to 4n plus 52. So there's my general term in the explicit form. And they want the sum of the sequence that includes 12 terms. So I'm thinking summation notation starting with n equals 1 until n equals 12, 4n plus 52. And I want you to go ahead, let's type that into the calculator, alpha F2, choice 2, see what you get. I got a big old bear of 936, and that is very ironic and accidental that our first two answers were both in the 900s. Alright, here's for our third problem tonight. And check this out. Have you ever seen a more innocent looking sequence in your life or series? I'll tell you, it's 4 plus 7 plus 10 plus ... plus 106. You're like, what could be more innocent than that? This is the biggest cupcake ever. But in the back of your mind, you're thinking, this is supposed to be harder than the previous question, right? That's how all these videos work. That's how every math assignment works. They get harder and harder as we go. So what's the catch? Well, I don't think we're going to really run into any major bear traps until part C. So with that being said, let's just jump in and get part A and B out of the way. What you'll notice just by simply looking at this rascal is that the first term is a 4 and your common difference is a 3 because that's how much is being added to each term. So part A says recursively a sub n is a sub n minus 1 plus your common difference, where the first term is defined as 4. Part B, we're saying that a sub n is the quantity n minus 1 multiplied by, whoa, should have put a 3 there earlier. How about that? Try a 3. Okay. Multiplied by 3 plus the first term. Let's go ahead and distribute and combine like terms. And we can say, well, a sub n is really 3n minus 3 plus my 4, which gives me 3n plus 1. Okay, bingo. There's my explicit nth term of this arithmetic sequence. And now I want to find the summation. From n equals 1, we'll use 3n plus 1. But here's the kicker. I don't know what goes right there. I don't know what the upper bound is. Now here's a common mistake. A lot of people like to put this 106 right here. But do you see the problem with that? Just because that's a 106, this doesn't mean that's the 106th term, does it? And that's where that begs the question, what term is this? Is this the 12th term? Is this the 15th term? Is it the 20th term? I've got no idea right now. I don't know what term that is. And so that's our job, or that's our task at hand, is to figure out which term within the sequence does the 106 represent. So let's play this game. Now, I better pull out a different color because this is big time work right here. We already know that the nth term is defined as 3n plus 1, right? Well, what if I substitute the 106 right here and I try to solve for n? So I would subtract 1 from both sides. And now I'm going to try to divide both sides by 3. Bang, bang. And 105 divided by 3. I'm going to double check this so I don't screw it up. 35 equals n. So here's what I'm trying to say, is that 106 is the 35th term within this arithmetic sequence, okay? So what that means is I want the sum of the first 35 terms, and I'm going to replace my question mark with a 35 right there, and then let's go evaluate it on our calculators and just make sure we got the same sum when we're all done. And I got a big old bear of 1,925 for the sum of the first 35 terms within this arithmetic series. But I tell you what, just like the last one, they don't get much more innocent looking than this one right here. And the good news is we instantly know that the first term is negative 35, so we don't have to go hunting for him. And we know that the common difference appears to be a positive 6. Looks like they continuously are adding 6 to get to the next term. So we've got those two locked down. So let's go ahead, let's take care of part A. Recursively, we know the nth term is going to be the n minus first term plus the 6, where the first term is defined as negative 35. Let's see. Explicitly, we've got the quantity n minus 1 multiplied by 6, and then we're going to add a negative 35. We'll go ahead and we'll distribute the 6 and combine some like terms. So we know the nth term is 6n minus 6 minus 35, or in other words, the nth term is 6n minus 41. Bang, right there. We're going to come back and use that bear. Because now we want the sum, we're going to start with the first term. We're going to use 6n minus 41, of course. Now the big $1 million question is, what goes right there? True or false? We want to find the sum of the first 73 terms. And the answer is a big old false, because this term, it's the last term 73, but that don't mean it's the 73rd term. And that's our task at hand, is what term number is that represented by right there. So just like the last question, we're going to tackle it the exact same way. We already know that the nth term is guaranteed to be 6n minus 41. So let's set the 73 right there, and we're going to solve for n, because again, n tells us what term number it is. Add the 41 to both sides. We get 114 equals 6n, and then we're going to divide both sides by 6. 114 divided by 6 is going to be 19. So 19 equals n. In other words, 73 is the 19th term within this arithmetic sequence. So let's go ahead, we'll splash a little 19 up here, and then we'll fire the summation into our calculator. And this time my sum of the first 19 terms was 361. Our last problem that we're going to wrap things up with tonight is a really nice investment style problem. It's going to give you a little taste of how this might apply to the real world. And so the story goes that Josh invested in a company called Gadget Inc. And the first year that he made his investment, his shares earned him a return of $1,250. Now, each year after that, his investment returned $200 more than the previous year. So, trying to describe that, his first year was $1,250. Let's see, his second year, he made $200 more than that, so he was at $1,450 that he got returned. And then on his third year, he made $1,650, etc., etc. Now, if this pattern continues, and he would be very fortunate if it did, of course, but how much would Josh make over the next 35 years? So, here's what we got cooking. We know who the first term already is. We know that the common difference is $200. So, I'm thinking explicitly anyway that the nth term is going to be n minus 1 multiplied by 200. Then we're going to add the original term 1250. If we distribute just like we've been doing, we'll know that the nth term is 200n minus 200. Whoops, almost forgot my n. Plus 1250. And we'll combine like terms to get 200n plus 1050, because this was a negative right there. Alright, so here's my nth term. We're ready now to add up how much he made over 35 years. And so now I'm going to introduce the summation sigma. We're going from 1 to 35. That's first year to the 35th year. And we'll wrap this bear up with parentheses. And then we're going to go evaluate it on our calculator. And any guesses before you type it in? It's always fun to make a prediction and see how close you are. I got $162,750, and that would be the total that he's made if we add year 1 plus year 2 plus year 3 all the way to the year 35. Not bad work right there for Josh. He can have a lot of fun with that. So I hope you had a good time tonight. And I hope you feel comfortable evaluating these on your calculator, and we'll catch you tomorrow.